Welcome back to online learning. We're going to look at galvanic cells and electrolytic cells today. We're going to do a worksheet on it. I really want to make sure you know how to draw the galvanic cell diagrams and maybe electrolytic cell diagram, even though we won't go too deep into electrolytic cells. So we're going to look at two types of cells, electrochemical and electrolytic. And electrochemical is most often referred to as a galvanic or voltaic cell. The AP test refers to them as electrochemical cells. And they are named galvanic or voltaic from two different Italian scientists who were the first people to construct the spontaneous electrical energy, Luigi Galvani and Alessandro Volta. And then we'll look at electrolytic cells, and you may need to access a standard reduction potential chart to do this. I will give you the information down here, but if you have that chart, you can see where that information came from. So below, draw and label a zinc and a copper galvanic cell according to these equations down here. And when labeling, use the following terms: the electron flow, salt bridge, sulfate ion flow, zinc ion flow, zinc and copper electrodes, zinc sulfate solution, copper 2 sulfate solution, cathode anode oxidation and reduction. We got a big task ahead of us. So let's scroll down, and this may be challenging to draw, just letting you know. So we need to draw some beakers or some cells. And we will start with a cell here. I may not be giving myself enough room. We'll do our best. And another cell. So galvanic, electrochemical, or voltaic cells are two separate cells or beakers, and they are connected by a salt bridge. Could also be that porous disc we saw yesterday. Look at this lovely salt bridge. It's a beauty, peeps. Let's put a little bit of solution in here. Oh, let's make it that color. There we go. And we need to put our electrodes in there. Oh, but before we do our electrodes, we have to look at these equations up here. I traditionally like to draw the cathode on this side. So we're going to draw these, and usually in textbooks you will see the anode on this side and the cathode on this side. But let's see what we get here. So we look at these two equations, and they are written as reduction potentials, and we have to flip one because electrons have to be on the opposite side. And then when we add these numbers up, it has to be a positive number. So if we flip the copper equation, we would have a negative 0.34, and a negative is a negative. That's not going to work for us. But if we flip the zinc one, we would have a positive number, and then we would add those numbers up, and we would get a positive number. So the zinc must be flipped to be a reduction, an oxidation, and this one remains this way to show reduction. So if we flip the zinc one, that'll be a positive, and then if we add those two up, we get 1.10 volts. And we would somehow or another in here put in a little voltmeter, and our voltmeter would read 1.10, that's a 0 volts. That looks terrible, doesn't it? And then we will connect that to our electrodes. And as I said, we usually, in most textbooks, they put the anode on this side and the cathode on that side. And I think we'll do that today. Let me erase some of this stuff. And so let's label which one would be which. So I always have to go back to what I know. An ox and a red cat. So at the anode, you get oxidation. So loss of electrons is oxidation. Reduction at the cathode, so that's gain of electrons. I like my Leo the Lion goes grr. So if you're gaining electrons, it is plus on the left-hand side of the arrow. And if you're losing electrons, it is a plus with electrons on the right-hand side of the arrow. So we said we were going to flip this one so that it was really zinc arrow, zinc 2 plus, this is some terrible writing, peeps, plus 2 electrons. So the zinc has the electrons on the right hand side, so that would be oxidation. So oxidation happens at the anode. So here at our anode, we are going to have the zinc stuff happening. And then at the cathode, we will have the copper stuff happening. And now I need to draw in my electrodes. So let's see. I don't really have a very nice coppered colored one. We'll pretend that's copper. And we'll finish connecting that wire to that one. And we will call that thing copper. So that one is solid copper. And this one over here is the zinc, and we'll do zinc in gray because zinc is kind of a grayish metal. And we'll say that that one is solid zinc. That's a solid. I'm going to get rid of that there now. And this one, and I think I'm going to get rid of this down here because it's cluttering it up, peeps. So have we labeled what we're supposed to label so far? So we have the anode and the cathode. I need to draw in color in my little zinc electrode. There we go. And we have our salt bridge, and we have our copper solid. We have our zinc solid. We need to show the flow of electrons. So the flow usually goes from the anode to the cathode. Do we have any other cool colors here? Maybe a purple. So the electron flow, I should really do this in a pen instead of that. Let's do that. The electrons flow that way. So if I do a little E with a minus and an arrow, so the electrons are flowing from the anode to the cathode. And we have our voltage up there that looks terrible. We can't read it very well. So the anode is going to be negatively charged, and the cathode is going to be positively charged because the anode is the source of the electrons flowing from here over to there. And so this part is going to lose weight, or its mass is going to decrease because we're losing electrons, and the electrons are going to collect over here, and this side will be gaining weight. So on this thing, we're going to start getting more stuff, and so on this we're going to have Cu2 plus adding 2 electrons, and it's going to make solid copper. So this is gaining solid copper atoms. So the mass is going up on this side. So the mass on this side is increasing. Meanwhile, on the other side, we have the mass decreasing. So the mass is decreasing. I like to use my arrows. What a lovely arrow that is on that side. And so on this side, what we have is zinc being oxidized into zinc 2 plus 2 electrons. There's some horrible stuff going on there. And so again, the electrons are leaving and going that way. And in the solution, then you'll have zinc 2 plus. And on that other side, you'll have some solid copper gaining there. This piece of equipment there that we drew is the salt bridge, so I labeled that the salt bridge. And now we have to say which way the ions are flowing in that. And we have to remember that in this cell, the electrons are leaving, so it's having a deficit of electrons. And over here, electrons are building up, so we're getting more and more electrons. So we need electrons to be replenished in this side, and on this side, we need to take away those excess electrons so we don't have too much of a buildup. And so what is in these solutions is on the left side is zinc sulfate. So it's really zinc 2 plus and SO4 2 minus. And then on the other side, we have a copper sulfate solution. So you really have copper 2 plus ions and sulfate ions. And so you have to ask yourself, which way will these sulfate ions go in the salt bridge? And what I missed in here, what is actually in the salt bridge? The salt bridge has, I don't think I put it up here. The salt bridge has sodium sulfate, NaSO4, Na2SO4 in the salt bridge. And so that's the positive part and that's the negative part. So the positive ions will be going this way, and those are the NAs. So the Na pluses are going this way. And to the other side are the SO4s. That's where I got my SO4s a couple moments ago. So the SO4s go to this side to replenish the deficit of electrons because they're leaving. And then over here, the Na pluses come and take some of those electrons so you don't have such a buildup of them. So let's recap. I erased it and I drew it all over again because that's what I do. So over here we have the anode and it is zinc, and over here we have the copper electrode and it is the cathode. And the anode is where electrons are lost, reduction is happening, so electrons flow from the anode to the cathode. And if you were to look at the voltmeter, it would be 1.10 volts, so we did plus 0.76 plus 0.34 volts, that's where we got the 110 volts. And in the salt bridge, to balance out the charge, the salt bridge had sodium sulfate in it. The sulfate ions, the negative ions, go here to replenish the electrons that are leaving, and then the sodium ions go here to take up the excess electrons that are building up over here. And so since solid copper is being deposited on here, the mass of this side of the cell is going up, and the mass on this side of the cell, since electrons are leaving, is going down. So let's answer some of these questions now. What is the charge of the anode? The anode is a negative charge. What is the charge of the cathode? It is a positive charge. And what side of the cell will increase in mass? It is the cathode, because that's where the electrons are going. And what side of the cell will decrease in mass? That is the anode. That's where the electrons are leaving. And then we need to write the line notation for this cell. And the last thing is we need to calculate the cell potential, and we already did that part, so I'm going to jump to that part. 0.76 plus 0.34 volts equals 1.110 volts. So the line notation will have the anode on the left-hand side and the cathode on the right-hand side. And so the anode was zinc, which was solid. And then we do a line, and then we had aqueous zinc, 2 plus, was aqueous. We would put in the molarity if we knew what it was. And then we do a double line, and then we have what's on the cathode side, which we had copper 2 plus, which was aqueous. And then we do a line, and then we were making solid copper. So that's the line notation, if you can see it in there. Now we're on page 2, Intro to Electrolytic Cells. So an electrolytic cell converts electrical energy into chemical energy. Electrolytic cells are not spontaneous. They need an outside source. And so electrolytic cells need an outside source of energy. This outside source can be a battery. It might be something that's plugged into an outlet. And the physical state of the species in electrolytic cells is liquid. A lot of times they use the word molten. And there is one container in an electrolytic cell as opposed to two very separate containers in a galvanic cell. And in an electrolytic cell, the anode has a positive charge because the electrons are leaving it, and the cathode has a negative charge because the electrons are going towards it. It's reversed of a galvanic cell. Now we're going to look at an electrolytic cell, and again, we haven't learned much about these yet. We're just going to dive into it. They can be a little bit confusing. So on here I have would like you to label the following parts on the diagram, both electrodes as inert, because having an inert electrode is an important thing in an electrolytic cell. If the electrodes are not inert, you have a whole nother equation going on, but we'll learn that in another time. Draw in the battery and use an arrow to show the flow of electrons. So let's look at this. So each of these electrodes are inert, so I put an inert electrode and inert electrode. And the battery, big dash, small dash, big dash, small dash, that's the battery. And then I showed the flow of electrons. They are still flowing from the anode to the cathode, but the anode for an electrolytic cell is called positive and the cathode is negative because the electrons are leaving here, so that becomes positive, and the electrons are being pulled here, so that one is negative. Now there's some other stuff going on here that relates to these equations up here. So number 2, look at the reduction potentials below, these ones, and label what is being produced at the anode and what is being produced at the cathode. To help with that, in electrolytic cells, the anion, think Cl for this, so this overall cell has NaCl in it. So Cl is the anion, is at the anode, and the cation is always at the cathode, and the cation in NaCl is Na+. So the anion and cation compete with the water, because they're in water, to make it aqueous. So if water is more likely to be reduced or oxidized, then you select the equation with the water. So the potentials are grouped together. For example, the Na plus would compete with the 2 waters and 2 electron equation, where the Cl2 would compete with the water that has the 4 electrons in it. And on an AP test, I think they would give these to you in groupings. So the reduction potential with the largest number is the reaction that takes place. For example, minus 0.83 is bigger than minus 0.271. And I'm looking at these here. So in this case, the 0.83, which is the water, would win out over that one. So you would choose that equation and ignore this one, which would mean that the Na part doesn't happen. Did I miss something else? So minus 0.83 is bigger than minus 2.71, so the water would be split into hydrogen gas and hydroxide ions, because that's what the equation says, rather than sodium being made. And the overall, the solution would be basic and turn pink in the presence of phenolphthalein. If phenolphthalein were dropped in there, they might ask you to prove, how do you know that it's basic? So you look at this equation, you see that OH is produced, and a telltale sign of a base is to add phenolphthalein, and it would turn pink. So we're going to look at these first 2 equations. So we pick either between this one or that one. Sodium is the cation, so this is what's happening at the cathode. And remember, it is in water, so you have to see which one actually is more likely to happen. And since the minus 0.83 is more likely to happen, sodium ions are not made into solid sodium. That would be too convenient, wouldn't it, just to be able to make your own solid sodium at a drop of a hat. So instead, the water adds the electrons, and it makes hydrogen gas and 2 OHs. And hence, over here, that's why hydrogen gas is subtly, you don't see it being bubbled out, and that's why that hydrogen gas is there. So now if we look at those other equations, so now we're going to look at these sets of equations happening at the anode. And at the anode, it's really loss of electrons is oxidation. So these would be flipped, such that on the right-hand side, you would really have chlorine gas being produced. And for the water one, you would actually have oxygen gas being produced. Since this number is the bigger number when they're in this direction, the chlorine equation is the one that happens. And if we look down here, you can see that the chlorine gas is actually bubbled out. So hopefully you can see that an electrolytic cell is different than a galvanic or a voltaic cell. A electrolytic cell is happening all in one cell. And if you remember that one day in class where I pulled out the U-tube, some of you may have been watching, some of you may not have been. I pulled out a U-tube, and in there I put in Ki, and I hooked it up to the battery, and the power source and had the source in there for both. And at one side, we actually produced iodine, and it collected at the bottom a really darkish, brownish red color. And then at the other side, the water was the one that was affected, and it produced OH ions. And so when I put in phenolphthalein, you could actually see it turn that phenolphthalein pink, which is not that color, but that's close. So this U-tube, even though it looks like two separate things, it's one cell, as opposed to, again, those galvanic problems that have two separate cells and they are connected by a salt bridge. I hope all is going well. I miss seeing you in class, and I'm sure I'll have another video for you in the future.